Here we want to analyze the characteristics of the function f of x and plot a graph of the function. So our function is 2x over the square root of x squared plus 3. So the first thing that I'm going to look at are to see if there are any vertical asymptotes. To determine if there are any vertical asymptotes, what I really need to ask myself is, are there any zeros in the denominator? So are there any zeros in the denominator? Well, the denominator, x squared plus 3, the square root of x squared plus 3. So the question would be, what values of x make this equality true? And x squared plus 3 has to be greater than or equal to 0 all the time. And if we were to try to solve for x, we can't, because we won't get a real number if we take the square root of -3. So what we can conclude is that x squared is always greater than 0. Oops. And therefore there are no vertical asymptotes. Having confirmed that there are no vertical asymptotes, the next thing I'll look for are any horizontal asymptotes. To check for horizontal asymptotes, what I really have to ask is, what are the limits at plus and minus infinity? To determine the limits at plus and minus infinity, I want to actually evaluate the limit, but I have to do a little bit of work to manipulate the function into a more convenient form. So 2x over x squared plus 3. And in order to analyze this irrational function, I want to let x be plus or minus the square root of x squared. So if I'm evaluating the limit at infinity, I would let x equal the positive square root of x squared. And if I'm evaluating the limit as x goes to negative infinity, I would let x equal the negative square root of x squared. And I'm going to essentially multiply the function by a convenient form of 1. So 1 over x in the numerator and 1 over x in the denominator. But instead of writing x, I'm going to write the square root plus or minus, let's redo that, plus or minus the square root of x squared. This is the same as saying 1 over x over 1 over x, or simply multiplying by 1. So this gives me 2, since the x's cancel here. And then, let's see, what do we get? 2 over plus or minus the square root of x squared plus 3 divided by x squared. So I can bring the x squared under the square root. And then I have 2 over plus or minus the square root of x squared over x squared plus 3 over x squared. And finally, 2 over the square root of 1 plus 3 over x squared. I have to remember this is plus or minus. And the important thing here is that when we take the limit, so I'll split it up this time, the limit as x goes to positive infinity is plus 2 over the square root of 1 plus 3 over x squared. So I'm going to take the positive value of the square root. And so as x gets really, really big, 1 over x squared gets small and approaches 0. And so the limit approaches 2 over the square root of 1, or simply positive 2. And let me see if I can shift things up a little bit here. If I evaluate the limit as x goes to negative infinity, take the negative value of the square root. Again, 1 over x squared as x gets really big, gets really small, and approaches 0. And so the limit is -2. And so I expect to have horizontal asymptotes at +2 and -2. And because this is an irrational function, I have a square root in the denominator, irrational function, I would actually expect to have two different limits. So as x goes to infinity, positive, the limit will approach +2, and as it goes to negative infinity, it'll approach -2. We haven't stated the domain yet, so the domain would be valid values that x can take on. And in this case, there are no restrictions on x. X includes all real numbers. What I would want to check is that I cannot have a negative value under the square root. I can't take the square root of a negative number. It gives me a non-real value. And so if I had, for example, x plus 3, then the values of x would be restricted to make sure that x plus 3 is always greater than or equal to 0. But because we have x squared, it will never be less than the square root of 3. So for that reason, x is basically unrestricted. For the range, we want to consider valid values of y, where y equals f of x. And in this case, the values of y are restricted by the horizontal asymptotes that we found before. And so in this case, the range will be bounded below by -2 and above by +2. So we have -2 to 2 as an open interval. For the x and y intercepts, we're interested in where the function crosses the x and y axis, and we can determine that by determining what the value of f of x is when x equals 0, or what the value of x is when f of x equals 0. And in this case, we have just one intercept, and it's shared x and y intercept. It's the origin, 0, 0. Now, last but not least, we need to determine if there are any critical numbers or potential points of inflection, and then we can evaluate the concavity of the function. So first, to determine if there are any critical numbers, I'm interested in if there are any values of x that make the first derivative, f prime of x, equal to 0, or for which the function is undefined or does not exist. So the first thing I need to do is to take the derivative of the function f of x. So f prime of x is the derivative with respect to x of 2x times, I'm going to bring the denominator into the numerator, and I can do that because 1 over the square root of x squared plus 3 is equivalent to a power of -1/2. To take the derivative, I can use the product rule. So I have 2x times this quantity raised to the -1/2. And for that, I'll need to use the chain rule. So the first is 2x, and the derivative of the second is -1/2 times x squared plus 3 raised to the -3 over 2. And then I have to take the derivative of the inside, x squared plus 3. So the derivative of that is 2x. And then for the product rule, I have the second term unchanged times the derivative of the first term, 2x, so the derivative is just 2. And now I need to simplify this. So these 2's will cancel, and I can write minus 2x squared divided by x squared plus 3 raised to the 3 over 2 plus 2 divided by x squared plus 3 raised to the 1/2. Now if I want to combine these two terms, I need them to have the same denominator. So I can multiply the second term by x squared plus 3, and that'll give me x squared plus 3 raised to the 3 over 2 in the denominator, but I can't change the function. So if I essentially multiply by 1, I can just manipulate its form a little bit. And so now I can combine the terms in the numerator. Minus 2x squared plus 2x squared plus 2 times 3 is 6. And this is all over x squared plus 3 raised to the 3 over 2. So finally, we have 6 over x squared plus 3 to the 3 over 2. And the question is, for what values of x does this derivative, f prime of x, first derivative, equal 0, or is it undefined? It does not exist. So are there values of x that satisfy that equation? So there are actually no values of x that will make the first derivative equal to 0. And if there were values of x that would make the function f prime of x undefined, it might be having a 0 in the denominator, but because x squared is always positive and we're adding 3, this will never equal to 0. And so the result is there are no critical numbers for this function, and that means that there will be no relative extrema. Our last task is to determine if there are any inflection points and evaluate the concavity of the function. And so to do that, we need the second derivative, f double prime of x. And the question is, for what values of x is the second derivative equal to 0 or undefined? And I'll write that as does not exist for short. So we need to take the derivative of the first derivative in order to get the second derivative. So d dx, the derivative with respect to x of f prime of x, is d dx, and the first derivative we found is 6, and I'll write it as x squared plus 3 raised to the negative 3 over 2. And here I have really just a power function with the chain rule. So I'll have the outside and then the derivative of the inside. So 6 times negative 3 over 2 x squared plus 3 raised to negative 3 over 2 minus 1 gives me minus 5 over 2 times the derivative of the inside term, x squared plus 3, is just 2x. And I can simplify this a little bit, and I should get minus 18x divided by x squared plus 3 raised to the 5 over 2. And so the question is, are there values of x that make this 0 or undefined, does not exist? This is the second derivative. And in this case, there is. The second derivative for x equals 0 will equal 0 because we have an x in the numerator. So the point 0, 0 is a possible point of inflection. And to determine if it is actually a point of inflection, I have to check the concavity. And so I can imagine dividing up the domain of x values around x equals 0. So I can test a value for x greater than 0 and less than infinity, and x less than 0 and greater than negative infinity. So I'll test x equals 1 and x equals negative 1. And the second derivative, evaluated at x equals 1, gives me minus 18 over 32, which is less than 0. And the second derivative, evaluated at x equals negative 1, gives me positive 18 over 32, which is a positive number. And really all I care about is the sign. So because the second derivative is greater than 0 in that interval, then the function f of x is concave up for x less than 0, and the function f of x is concave down for x values greater than 0. So at this point we've evaluated all the characteristics that we need to know about this function in order to plot it. So the last thing I'm going to do is actually graph the function. Go back, I want to point out that we said 0, 0 was a possible point of inflection. And when we determined that the function switches from concave up to concave down at that point, that makes x equals 0 is an inflection point, or a point of inflection point, because that is where the concavity switches. The first thing I want to do is highlight the key features that we identified, which is that the x and y intercept is at the origin, and I have an upper bound or a horizontal asymptote, which is the upper bound, which is at positive 2, and try to make this symmetrical, a lower bound, another horizontal asymptote at negative 2. And I also determined that the function will be concave up for values of x less than 0. So the function will look something like that, and then it passes through the origin. The origin is also a point of inflection, and then it's concave down for values x greater than 0. So use your favorite graphing utility and check this, but I think you'll find out that it matches.